Hello everyone, myself Dr. Ranjith Kumar Gatla, working as an associate professor in the Department of Electrical and Electronics Engineering. In today's class, we are going to discuss about the definition and terminology related to the network theorems. So, in this class, we are going to discuss various network theorems. Okay, the exact what the network theorems defines, the definitions. Okay, and also we will see. Okay, so the procedure to apply these network theorems also. So the various networks theorems that we are going to discuss in this class are the basic network theorems, which are superposition theorem and maximum power transfer theorem, Thevenin's theorem, Norton's theorem, and Millman's theorem, compensation theorem. So these are the various theorems that we are going to discuss in this today's class. So first, let us start with the superposition theorem. So define superposition theorem, because you will get some questions based on the definitions and terminology also in your final examination. Define superposition theorem with a suitable example, something like that. You may get the question in your final examinations. So in that case, you have to write the statement of the superposition theorem, and you have to consider one example, and you have to prove that superposition theorem, which means you have to apply the superposition theorem for a particular network. Okay, and then you have to prove that superposition theorem. So, according to the superposition theorem, if the superposition theorem defines, or the superposition theorem states that in any linear active bilateral network. So here the word that as you can see, the superposition theorem can be applicable only for the linear active bilateral networks. So we already discussed these theorems, okay, but here what is mean by the linear network, and what is mean by the active network, and what is mean by the bilateral network. So here linear means if the elements present in the network having the linear in nature, then we can call it as that particular network is the linear network. Then when coming to the active, means here some elements are, as we know, active elements and passive elements. So active elements are nothing but the voltage source and current source, which means electrical network that must contain at least one voltage or current source. And the bilateral, which means here, as you know, the current flowing through the device can be allowed in both the directions. So which means that particular elements are called as the bilateral elements. So here this superposition theorem states that in any, okay, it should be a linear active bilateral network having more than one source. Okay, so which means here this theorem is applicable to the networks, okay, those who are having more than one source. The response across any element, okay, the response here, it is nothing but either it may be voltage or it may be current. Okay, so the response across any element is the sum of the responses obtained from each source considered separately. So suppose let us consider, because here this particular theorem is applicable, okay, for the networks those having more than one source, either it may be voltage source or it may be current source. So which means, suppose let us consider a particular network having three sources. Then in that particular network, suppose if you want to find the response across any element, which is equal to the sum of the responses obtained for each source considered separately, which means initially, considered separately, and the other sources are replaced by their internal resistances, which means suppose if it is a voltage source, then the voltage source is replaced by this internal resistance, or the voltage source is replaced by the short circuit, and the current source is replaced by the open circuit. So in that way we will find, then you will get the response across that particular element in the three cases by considering three sources independently. Then the the response, okay, across an element in the actual circuit is equal to the response obtained from each source considered separately. Okay, the sum of the responses obtained from each source considered separately. So this is the statement of the superposition theorem. And here, which means, suppose here there is a simple circuit, this simple circuit having the two sources, one is the voltage source Vs, another one is the current source Is, right? And suppose let us consider, we need to find the current flowing through the resistor R3, which is I, right? Then according to superposition theorem, okay, the sum of the responses obtained from each source considered separately. So which means first let us consider only the voltage source, okay, and the other sources are replaced by the internal resistances, which means if it is a current source, then the current source must be replaced with the open circuit, and if it is a voltage source, then the voltage source must be replaced with the short circuit, right? So here, of course, there is a current source, so that's why here we are replacing the current source with the open circuit, right? then then find the current flowing through these R3, which is, let us consider I1, right? So then in the next case, we have to consider only the current source independently, and the voltage source is replaced with the short circuit, right? So here, now in this case, this is the voltage source, we have removed the voltage source, and this voltage source is replaced with the short circuit. And now again find the current flowing through the R3, let us consider here it is I2. Then the total current or the current I is equal to I1 plus I2. So this is what the superposition theorem states, which means the response across any element, the response across any element is nothing but the response across, let us consider the current flowing through the R3. I is some of the responses obtained from each source considered separately. So here first, the voltage source only we considered separately, and other sources, if because other source is current source, so the current source is replaced with the open circuit. Then we got the current I1. Then in the second case, okay, so we considered only the current source, and the voltage source is replaced with the short circuit, and we find the value of I2 again, the response in the same element, then it is I2. Then I is equal to I1 plus I2. This is about the superposition theorem. Then for example here, you can consider, okay, one example, the practical example here. So here this is a source, of course, this circuit is also having the two sources, one is the voltage source, another one is the current source. And here, of course, first let us consider here V32 is the acting source, here V32 is the acting source, and this 2 ampere is replaced with the open circuit. Now we need to find the current flowing through the 3 ohms resistor according to the given problem. So here 3 ohms resistor is this one. So we need to find the current flowing through this 3 ohms resistor. So let us consider in this case the current flowing through the 3 ohms resistor is I1. Okay, then by applying simple the loop analysis, we can find the current, the loop current in the first loop and the loop current in the second loop. So just apply. Okay, so let us consider here the current flowing through the first loop is I32, and the current flowing through the second loop is I1. Now write the mesh equations. Okay, so this is the mesh equation for the first loop, and this is the mesh equation for the second loop, and solve these two equations. Then you can find the current flowing through this loop and the current flowing through this loop. So then here, of course, we got the value, the current flowing through the 3 ohms is I1, so I1 is equal to 3.428 amperes, right? Then similarly, in the second case, okay, let us consider here the 2 amperes current source is active source, and the voltage source is replaced with the short circuit. Now also let us find the current flowing through 3 ohms resistor. So in this case, okay, to simplify this again, we know these two, okay, here the 4 ohms and 12 ohms are in parallel. Then this combination can be replaced with the equivalent resistance, which is 4 into 12 by 4 plus 12, so which is equal to 3 ohms, right? Then here we can replace these, we can convert these current source into the voltage source. Okay, so then if we can convert, that is the source transformation, then it will become the 6 volts in series with the 3 ohms resistor. Now you can find the current I2, which is equal to 6 by 3 plus 1 plus 3, are they simply loop analysis. I2 is equal to 6 by 3 plus 1 plus 3, which is equal to 0.857. So then I2 is equal to 0.857. Then the total current flowing through, the current flowing through the actual circuit in the main circuit 3 ohms, which is I is equal to I1 plus I2. So here substitute the values of I1 and I2, you will get the current 4.285. So which is the same like here, because so this is how we can apply the superposition theorem to find the response across any element. Then now we are going to the second theorem, which is the reciprocity theorem. So here, according to the reciprocity theorem, states that the value of the current due to the single source, the value of the current, okay, due to a single source in any particular branch of the circuit is equal to the value of the current in the original branch where the source was replaced when the source is shifted to a particular branch of circuit. Which means here, to better understand, let us consider one simple example. So here, this is the circuit. Okay, in this circuit here the voltage source is in series with R1. Okay, so let us find, let us take another circuit here and just have shifted this voltage source. Okay, from this particular branch to here. Okay, so let us consider here the current flowing through this what is that, the resistor R5 is I. Okay, and then let us find here, because from which branch we have taken this voltage source from the R1 branch. So then let us consider the current flowing through R1 branch is I1. Okay, then here I is equal to I1. This is about the reciprocity theorem, which means here again you just read one statement one more and apply, try to get understand by using these two circuits. Okay, according to the reciprocity theorem, so here the value of the current due to single source, okay, because here of course this is the single source in any particular branch. Okay, let us consider here this V is connected to this particular branch, okay, of the circuit. Okay, is equal to the value of current in original branch where the source was replaced. Which means here the value of the current due to single source in any particular branch of the circuit. So let us consider here R5. Okay, so this is the branch that we are considering the current flowing through R5 is I, which is equal, the I is equal, okay, equal to the value of the current in the original branch, because the second circuit, okay, actually where is the value, the voltage source is replaced from the original branch. This is, so then the current flowing through this original branch, okay, original branch where the source was placed, okay, before here it is the placed, so is shifted, okay, to a particular branch of the circuit. Because from where we considered I, we have to shift that source to that particular branch. So that's why here we have shifted to here. So then I is equal to I1. So here for this also let us consider, again here this now we know this is the voltage that we are shifted from one branch to another branch, and this is the I that we have calculated in the these two branches. Then the ratio of this voltage and this current is known as the transfer resistance. Okay, now let us take one example here. So the same example, but we have considered instead of R1, R2, R3, we have considered the resistor values. So let us consider here the current flowing through this 3 ohms resistor is I, and the current flowing through this 2 ohms resistor is I1. And then find the current I and I1 in these two circuits. Then let us see whether I is equal to I1 or not. Okay, so again here also simple, some loop analysis we are applying. Okay, so here these are the loops, and write the loop equations for these two circuits, then solve these two loop equations, then you will get current IA is equal to 1.08 and here I is equal to 0.38. Then similar way here also apply the loop analysis for these two circuits, for these two loops, and then write the loop equations, and then solve these two equations, then you will get I1 and IB value. As you can see here, the value of I, which is equal to 0.387 amperes, and the value of I1 is equal to also 0.387. So this, which means here I is equal to I1, which is equal to 0.387. So this is the proof for the compensation theorem, right? And of course sometimes maybe they ask us by applying the compensation theorem, okay, what is the transfer resistance? Then as we know already, V that they have given in the problem and I we have calculated, then V by I is equal to 25.83 ohms. So here the 25.83 ohms is the transfer resistance between these two circuits, right? Then the same reciprocity theorem, suppose if we are having, then define the Thevenin's theorem. Right now we are going to discuss about the Thevenin's theorem. So here this Thevenin's theorem, it is very simple. Okay, so of course this is also for the Thevenin's theorem, it is any linear or bilateral networks, and one more thing here, this what is the theorems can be applicable for both AC and DC networks, right? And the procedure for the AC and DC networks is same, and the definition for the AC and DC networks is also the same, right? Okay, so here, according to the Thevenin's theorem, it states that any linear bilateral network containing several voltage, currents, and resistances can be replaced by just a single voltage source in series with a single resistance connected across the load, which means, so in another word, simply we can say the given circuit can be replaced with the Thevenin's equivalent circuit, and the Thevenin's equivalent circuit is consisting of a V Thevenins in series with the R Thevenins and as well as the load, or the series combination of V Thevenins and R Thevenins is connected across the load resistance. Okay, so then that is called as a, I mean, by using that we can find or we can apply this Thevenin's theorem, right? Then of course there are some conditions to find, I mean, then we have to calculate the V Thevenins and R Thevenins. Okay, so for that let us uh, consider, so let us consider here it is a linear and bilateral network. Okay, and this total linear and bilateral network is replaced with a series combination of the V Thevenins and R Thevenins across this load, because here the load we are not disturbing and RL is there, just we are replacing this total linear and bilateral network other than the load as a the series combination of the V Thevenins and R Thevenins. This green color portion is replaced, right? Then how to find these V Thevenins and R Thevenins? So here again the V Thevenins, that is okay. So for that let us consider one simple example, right? So here we have to find the current flowing through this 3 ohms resistor by using the Thevenin's theorem. So according to the definition, so what we have to do, we have to replace, I mean, let us consider here this is the RL, okay, the load resistance, and the remaining, the total part here, the remaining this part has been, this part should be replaced with a series combination of the, what is that, V Thevenins and R Thevenins. So like that we have replaced. So this total circuit is this. We are replaced with this green color portion, right? So again RL is nothing but here it is 3 ohms, right? Now we have to find the V Thevenins and R Thevenins, then substitute in this equation, then you can find what is that, the value of I. So how to find the value of I? So I is equal to then V Thevenins by R Thevenins plus RL. Okay, so by using this we can find the current flowing through this 3 ohms resistor. Then first let us find the V Thevenins. Okay, first R Thevenins. So first we should know, okay, where we should find the R Thevenins and how we should find the R Thevenins. So where means across the load terminals, and how means while finding the R Thevenins, okay, we should replace all the active elements with the open circuit or the short circuit, which means if it is a voltage source, then we should replace it with the short circuit, and if it is a current source, then we should replace it with the open circuit, right? Anyway, here we are having only one voltage source, okay, so we should replace it with this the short circuit. Then find the equivalent resistance between these two terminals. Let us consider A and B. So of course here 4 and 5 are in series, I mean parallel. Okay, then the combination is in series with the 2 ohms resistor, so that here the total R Thevenins is equal to 4.22 ohms. Then now we have to find the V Thevenins. For the V Thevenins, here also, I mean, where and how. So where means again across the load terminals only, and how means, okay, I mean just open circuit and find across the this open circuit. Okay, so that's why here this is also called as a open circuit voltage, right? So then of course simply apply the what is that I, okay, because here the 2 ohms resistor is connected to open circuit, so that's why the current flowing through this is equal to 0. So that's why here let us consider I1 or I2. So that's why here the V Thevenin's voltage across these two terminals is nothing but the voltage across the 5 ohms resistor. So that's why here voltage across the 5 ohms resistor is 11.11 volts. Then V Thevenin's is equal to 11.11. Then substitute R Thevenins and V Thevenins in this circuit and find the current flowing through this particular circuit. I is equal to V Thevenins by R Thevenins plus RL, right? So then I is equal to V Thevenins by V Thevenins by R Thevenins plus RL. then here I is equal to 1.538 amperes. So then the current flowing through this 3 ohms resistor is 1.538 amperes. So this is how we can apply the Thevenin's theorem. Then next, the define Norton's theorem. So here the Thevenin's theorem and Norton's theorem having some similarities, because here uh, as you can just compare the Thevenin's and Norton's theorem. So in the Thevenin's theorem, of course, we have replaced the total linear bilateral network as a what is that, a series combination of the V Thevenin's and R Thevenin's. So, but here it is a parallel combination of I Norton's and R Norton's, right? I Norton's and R Norton's, right? So, which means here, as you can see here, this total circuit is replaced with the parallel combination of I Norton's and R Norton's, according to the Norton's theorem. Then how to find I Norton's and R Norton's? Of course, here again we are considering the same example. So to find the R Norton's, it is the same principle as a R Thevenin's. So we should open these two terminals and find R Thevenin's or R Norton's across these two terminals, and all the active sources must be replaced with the voltage, I mean short circuit or the open circuit. Then here Rn value is equal to 4.22 ohms. And similarly, but coming to the here, what is that? The short circuit current I Norton's is nothing but, because I Norton's, okay, so before V Thevenin's we have replaced, I mean open circuit across these two terminals, and we have replaced load as a open circuit and find the open circuit voltage. And here we are replacing this load as a short circuit, and we are going to find the current flowing through that short circuit. So that's why this is also called as a short circuit current. So that's why here we are just replacing with the short circuit and find the current flowing through the short circuit. So let us consider IN, then applying the loop analysis and write the loop equations and solve these loop equations, then you will get the IN value. So IN is equal to 2.631. Then substitute this in this value in this particular equivalent circuit, the Norton's equivalent circuit. Then find the current flowing through RL. Okay, so by simply applying the current division rule. So by applying the current division rule, we can find the current flowing through the 3 ohms resistor, which is equal to 1.538. Right. So in the previous case also the same value, and here also the same value. Of course, you will get the same value, because here finally what we are going to find, in the same circuit we are finding the current flowing through the 3 ohms resistor. But in the one case we have used Thevenin's theorem, and another case we have used the Norton's theorem. That is the only difference. And next, maximum power transfer theorem. So here the maximum power transfer theorem is also, I mean, more or less the procedure is same like in the Thevenin's theorem, but the thing is, okay, at what condition the maximum power will flow, that will defines the maximum power transfer theorem. So here the maximum power transfer theorem states that, of course, here the maximum power transfer theorem also can applicable only for the linear bilateral networks. So maximum power is delivered to the load when the load resistance is equal to the internal resistance of the source, which means when the load resistance equal to the the Thevenin's resistance, okay, then at a particular case the maximum power will flow through that particular load. That is states that the maximum power transfer theorem. Okay, so then let us take one example. Okay, so here we need to find RL value. Okay, we don't know the RL value. Find the load, the value of the RL when the maximum power is delivered to the load. Okay, so according to this maximum power transfer theorem, when RL is equal to R Thevenin's, then the maximum power will flow through the particular circuit. So which means now we have to find here the R Thevenin's, right, for a particular circuit. So then these R Thevenin's, how to find we already know the procedure. Okay, so where we have to find the R Thevenin's, then here we have to find the R Thevenin's across these two terminals, across the load terminal, and we have to replace the voltage source as a short circuit and find R Thevenin. So because here 6 and these 6 are in parallel, okay, so then you will get 3 ohms. Then here the 3 and 2 are in series, okay, then you will get 5 ohms, and the 5 and 5 are in again parallel, then you will get 2.5 ohms. So RL is equal to 2.5. And find the maximum power also. What is the maximum power flowing through the R5? So then for that we need to find VOC, okay, and V Thevenin's. Then again V Thevenin's, as we know already how to find. Then here the maximum power, okay, by using this equation we can find the maximum power, which is P is equal to Vs square by 4R. So Vs means here V Thevenin's, which is 1.5. Vs is 1.5, okay, and then P is equal to Vs square by 4R. So here Vs is equal to 1.5 and R is nothing but here, as we know, RL is equal to Rs, okay, which is equal to R, which is 2.5. Then substitute in this equation, then you will get the maximum power is 0.225 watts. Okay, so here by using the maximum power transfer theorem, by using that condition, we can find the load resistance as well as what is the maximum power that is flowing through that load resistance. Also, we can calculate by using this maximum power transfer theorem. And next, define the Millman's theorem, okay, which is also called as a parallel generator theorem. So according to the Millman's theorem, okay, it states that when a number of voltage sources are in parallel having with the linear internal resistance respectively, or the number of current sources are parallel with their internal resistances respectively, which means either a voltage source, because as we know, the internal resistance for the voltage source is connected in series with the voltage source, and the internal resistance for the current source is connected in parallel with the current source, right? Then respectively, then the arrangement can be replaced with the single equivalent voltage source in series with the equivalent resistance, or the single equivalent current source parallel with the equivalent resistance, right? So which means here this theorem is something like that. It is a combination of Thevenin's and Norton's theorem, because in the Thevenin's theorem also, what we have done, we have replaced the old circuit with the one what is that equivalent voltage source with their internal resistance connected in series. And in the Norton's theorem, we have replaced the old circuit with a single equivalent Norton's current, okay, in parallel with the internal resistance of that particular current source, okay. And here, as you can see here, this is what, suppose if it is a voltage sources having their internal resistances, then this is a, suppose let us consider a current source with the internal resistance, okay. So then this can be replaced, I mean this circuit can be replaced then this circuit can be replaced with this like this, okay, and this circuit can be replaced with like this. This is about the Millman's theorem. Then how to find V and R and I and R, that already we have discussed in the previous class, the procedure to find here V and the procedure to find R, and here also the procedure to find I and the procedure to find R, okay. So by using that procedure, we can find V and R. So that again here in this circuit, suppose if you want to find the current flowing through RL, okay, then again here I is equal to, let us consider here it is I is equal to V by R plus RL, okay. And here suppose if you want to find the current flowing here, here already I is there, let us consider IL. So here IL is equal to I into the opposite resistor, here it is R by R plus RL. So by using these two equations, we can find the current flowing through these two circuits. So this is about the Millman's theorem, right? Then coming to the, yeah, that is what, how we can find V and R, okay. This is the equation to find V and R, okay, the actual V. Then coming to the compensation theorem, okay, according to the compensation theorem, the again of course it is also a linear time invariant network, okay, that in a linear time invariant network, when the resistor RL of an uncoupled branch carrying current I is charged by delta R or R delta, okay, then the current in all the branches would be changed and can be obtained by assuming that the ideal voltage source has been connected such that Vc is equal to delta R in series with RL plus R delta when all other sources in the network are replaced by their internal resistances. So which means, suppose if this is a circuit, okay, so in this circuit, let us what is that replace some delta, I mean let us consider the current flowing through RL is I, the current flowing through RL is I. Then here, suppose if you replace a small change in resistance, which is, let us consider R delta is connected in series with this again RL, and find the current flowing through again here, let us consider it is I dash, and then again you just replace this voltage source, okay, to where to which branch you have added the change in resistance, which is delta R. So in this circuit, so RL plus this delta R that we have considered is equal to, okay, and here the VC is equal to I into delta R that we should replace. Then here the current flowing through here I is equal to, okay, here I delta. So which means I delta is equal to I minus I dash. So this is all about the compensation theorem. So already we have discussed how to apply the compensation theorem and what is the procedure to apply the compensation theorem and how to prove the compensation theorem, that is in the previous classes. So that's why here I did not consider example for this compensation theorem. So this is all about the definition and terminology in the network theorems. Okay, so because here already the various definitions and terminologies in these particular network theorems we have already discussed in the previous modules, because here as we know already what is mean by the linear network and what is mean by the bilateral network, okay, and what is mean by the active sources and what is the active elements and passive elements. Okay, so these all are we have already discussed in the previous module, so that's why I didn't discuss again the basics. Okay, so directly I have gone through the basic definitions of the various theorems that we have discussed earlier, okay, with some suitable examples. So which means here if you get a question in your final examination like define the compensation theorem and or define the compensation theorem and prove the compensation theorem by considering a suitable example, something like that, you may get the question. So in that case you have to what is that define the theorem, okay, and as well as you have to explain the theorem by considering any one of the examples, okay, according to your wish. That this is all about the definition and terminologies in the network theorems. So we'll meet in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.